Hi there. In this video, we're going to talk about what is the Poisson distribution, where it comes from, and what it's used for. In many textbooks, online resources, and YouTube videos, it's not actually explained how the Poisson distribution comes about. So in this video, I'm going to give an overview and try and answer these questions. To briefly answer the first question, what the Poisson distribution is simply a probability distribution that models rare events. The emphasis here is on rare events. It has the form lambda to the power k divided by k factorial multiplied by e to the power minus lambda. In this form, lambda is an average. It's a constant that's defined in a certain way, and it represents the expected number of events. And throughout the course of this video, I will explain how this is defined and how it's actually used in the Poisson distribution. When we say the expected number of events, we mean a distinct number of outcomes of something. For example, lambda could represent the number of typos in a book or the number of faulty products from a production line. You might be thinking, what do I mean by a rare event? How is the number of typos in a book a rare event? Well, a book might contain hundreds of thousands of letters, yet only have one or two or three typos. So compared to the total number of letters in a book, the number of typos is actually very small. That's why we say it's a rare event. The same is true from a production line. A large factory might produce millions of units of a certain product per year, yet comparatively, just a few might be faulty. So at this point, the main takeaways that I would like you to note down is what the Poisson distribution looks like, what is lambda, and the fact that the Poisson distribution is used to model rare events, like the number of typos in a book. So please note down these three main takeaways. What we're now going to look at is where does the Poisson distribution comes from and why does it look the way it does. A major question we want to answer in this video is where it actually comes from. Well, very simply, the Poisson distribution actually comes from the binomial distribution. The last video I did was on the binomial distribution, so I encourage you to watch it if you are unfamiliar with the binomial distribution. But basically, what the binomial distribution does is model the probability of a certain number of outcomes in a fixed number of independent trials n, each with the same probability of success, which is designated by the small letter p. So again, I want to emphasize that if you want to understand how this equation comes about, I encourage you to watch my last video on the binomial distribution. So proceeding forward, how do we get the Poisson distribution from this? Well, what we do is we consider a very special case of the binomial distribution and apply three specific assumptions to this equation. The first assumption is that the number of trials n is very large compared to the number of outcomes. Earlier, I gave the example of the number of typos in a book. The number of outcomes we said is small in that there are just 2 or 3 typos per book, while the total number of letters in a book is in the hundreds of thousands. So here, the huge number of letters is represented by the number of trials designated by the letter n, which we see is a large number. The second assumption is that the actual probability of the particular outcome is very small. So again, using the example of a typo in a book, if we consider 2 or 3 typos per 100,000 letters, then we can intuitively understand how there is a very low probability of just opening a book at random and immediately seeing a typo. The third assumption has to do with lambda, which you would have noted from earlier means the average rate of outcomes. So lambda is assumed to be a constant and does not change with either time or space. It's defined as the product of the number of trials n and the probability of a particular outcome p. This implies that p is equal to lambda over n. For example, if you expect 3 customers to arrive at a store per hour, this rate remains the same regardless of whether you take the hour and divide it into minutes, seconds, or even smaller intervals. If we divide 1 hour into 60 intervals, and since there's 60 minutes in 1 hour, then we are specifying n to be 60. This means that the probability of getting a customer in a 1 minute interval is equal to 3 over 60, which is 0.05. We can also choose to split the 1 hour into 3,600 intervals. Since there are 3,600 seconds in 1 hour, here the probability of getting a customer in a 1 second interval is equal to 3 over 3,600, which is just 0.00083. The moral of this story is that it is very important that lambda should be a constant because it ensures that the distribution accurately models real-world processes where rare events occur at a predictable average rate. What we're going to do now is derive the Poisson distribution from the binomial distribution using our definition of lambda. The first step is to substitute p is equal to lambda over n into the equation of the binomial distribution as can be seen on the screen. Wherever there's a small letter p, we replace it with lambda over n. The next step is to remember how n choose k is defined. You would see that the first term in the binomial distribution is n choose k, and we're now going to simplify that. So n choose k is defined as n factorial divided by n minus k factorial times k factorial. We then expand the numerator n factorial as n into n minus 1, n minus 2, all the way to n minus k factorial. The n minus k factorial both cancel in the numerator and the denominator. This then simplifies approximately to n to the power k divided by k factorial. The reasoning uses the fact that one of our assumptions was that n is very large. So n minus 1, n minus 2, etc. might as well just be n. If n is so huge, the order of magnitude of n is not going to be affected or change much if we just subtract 1 from it. So n minus 1 just might as well just be n. We can understand this entire simplification by just substituting in some numbers as a simple example, such as perhaps the number of ways we can choose 3 objects from a list of 10. We would write this as 10 choose 3, which is 10 factorial divided by 7 factorial times 3 factorial. We can then expand the numerator, 10 factorial, as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we see that in the numerator, we can then isolate the 7 times 6 times 5 times 4 times 3 times 2 times 1, and we can just write that as 7 factorial. And we can see now that the 7 factorial in the numerator will cancel with the 7 factorial in the denominator. And then what's left in the numerator, the 10 times 9 times 8, can then be approximated as 10 cubed. Perhaps this approximation isn't very accurate in this example because 10 is not a very large number comparatively. However, as I said previously, our assumption in the general case is that n is a very large number. So all of this was to show how n choose k can be approximated as n to the power k divided by k factorial. At this point, we have expressed the binomial distribution in terms of lambda, as can be seen on the screen. And we have just now shown that n choose k can be approximated as n to the power k divided by k factorial if we assume n to be very large. We now want to isolate the term 1 plus lambda over n to the power n minus k. We have already spoke about the assumption that n is large, so that means that the exponent n minus k in this term can be approximated as just n. If you have done first year calculus at university, this expression might look very familiar to you at this point. And the reason for that is that if we take the limit as n approaches infinity of 1 plus x all over n to the power n, then we find that this is equal to the exponential function e to the power minus x. If you want to verify or understand this result, then you can consult any of your first year calculus texts and you'll see how this is the case. So what we do now is just the same thing for 1 minus lambda over n to the power n as exponent. However, instead of x, we have lambda. We have made the assumption that n is very large, or in other words, n is approaching infinity. Therefore, this particular term is just e to the power minus lambda. So we can now take all of these simplifications and approximations and substitute them all into the binomial distribution. And what we see is that n to the power k will cancel off in the numerator and the denominator. And we are left with the final form of the Poisson distribution that I showed you earlier on. So this is how the Poisson distribution is derived, and this is actually where it comes from. What we're going to do is apply the Poisson distribution to a very simple example. So imagine a communication satellite in orbit and it being vulnerable to small meteoroid impacts. So on average, the satellite experiences 1 meteoroid strike every 6 months. So that means lambda is equal to 1. That's 1 strike per 6 months. This satellite can withstand up to 2 strikes in 6 months without failure. But a third strike in that period will cause a catastrophic failure. So what this is saying is that the satellite can only withstand up to 2 strikes from a meteoroid in a 6-month period. So the question that engineers will want to answer is, what is the probability that the satellite survives a 6-month period? So what is the probability that a meteoroid will strike this satellite at most twice? So we have derived the Poisson distribution as has been presented. Lambda is equal to 1, and the satellite will survive if k is equal to 0, 1, or 2. So what we are doing to answer this question is that we are calculating the probability with k less than equal to 2, which is the sum of the probabilities of k equal to 0, 1, and 2. So all we do is just take the Poisson distribution and simply substitute lambda is equal to 1 and k is equal to 0 for the first term, k is equal to 1 for the second term, and k is equal to 2 for the third term. Computing all of this gives us 0.3679 plus 0.3679 plus 0.1839, which equals to 0.9197. So what this means is that there is an approximately 92% chance that the satellite will survive 6 months and an 8% chance that it won't. An 8% chance of not surviving 6 months might seem low, but if the satellite costs in the hundreds of millions of dollars, then perhaps space engineers might see this level of risk as too high and might want to take proactive measures, like maybe adding some protective shielding to the satellite or maybe moving the satellite to a low risk region of space. So in this video, we've explored what the Poisson distribution is, why it looks the way it does, and how it's used in the real world. It's a simple but very powerful tool to model rare random events. So if you found this video helpful, please like and subscribe for more content like this. And let me know in the comments if you have any questions or want to explore related topics. Thank you very much.